Fabian. So I'm here today to talk about managing arrays for science applications at scale. Now, as many of you know, science is becoming increasingly data-driven. For example, last year, the Large Hadron Collider, which is used for particle physics experiments, produced 25 petabytes of data. But they couldn't even keep most of it. They don't have the tools to curate it or to query it or to really work on it. And this is hard because it makes it so that they can't easily go back and trace through their experiments or easily share data with others. It's just at too big of a scale. And this problem is only going to get worse. For example, in 2000, the Sloan Digital Sky Survey went online. And during this is a telescope that's used in a variety of astronomy labs. And during its first decade, it produced only 25 terabytes of data. And that's very manageable. But its successor, the Large Synoptic Survey Telescope, will produce 75 petabytes of data in the same amount of time. So it's several orders of magnitude increase in data, which they will need to manage and query, as well as disseminate the results from. Making this matter even more challenging, scientists access their data in a way that's not compatible with standard commercial databases. When they issue queries, they're doing complex analytics such as a fast Fourier transform or matrix multiplication. They are not working as directly, like with a relational database, you have a single table. It consists of a list of rows. You might have multiple tables, but each one is an independent object, and it's just a one-dimensional, unordered set. Whereas here, we're doing more spatial querying, so order matters a lot. And optimizing the data for these types of complex query workloads is crucial. Now, as you can imagine, arrays are everywhere. As a scientist pans her telescope across the evening sky, she produces lots of images, one after another. These are all two-dimensional. Climatologists, when they model the environment, work in three-dimensional space. So because they are collecting the data in this context, they want to be able to access it in a manner close to, and reason about it in a manner close to how they work. So reasoning about arrays is quite important. Another feature of science applications is that skew is very prevalent. The stars are not evenly distributed through the skies. Whales migrate in pods, and people congregate in cities. And this Zipfian or power law distribution is found in virtually every scientific discipline. So when we think about this in terms of arrays, this means that parts of the array might have a lot of samples, and others may be very sparse. So because skew is so prevalent, and it has this exponential drop-off, it creates new challenges for optimization. Now, when I talk about this Zipfian skew, I mean that, for example, with US cities, the top-ranked cities will have a population of n, and the second-ranked ones will have a population of n over 2, third n over 4, and so on. So we have this precipitous drop in where the data is concentrated. So yes?
Can I ask what y-axis is?
What?
Y-axis is?
What the y-axis is? So the y-axis here is the size of, this is a probability density function. So the y-axis is the percentage of the data that resides up here. And so let's talk about how we solve these problems right now. So if you have very simple data and you're only performing straightforward analytics such as averaging your data or selecting a subset, then you might use Postgres or MySQL. These are standard relational solutions. And if you need to scale out, people often turn to Hadoop or Spark, which are great for, again, doing massively parallelized execution, but geared for more embarrassingly parallel applications where there are limited dependencies among the data. And there's also, for complex analytics, the most commonly used tools are R or MATLAB. And these are good because they have off-the-shelf implementations of things like matrix multiplication or statistical algorithms. But on the other hand, they're designed with the idea that the data will fit in memory, and that's just not holding true anymore. It's growing too quickly. So, but they are geared for this iterative access of the data as for the linear algebra type case. Now, the system within which I work is SciDB, and this is designed for complex analytics at scale. So it's distributed and it's an open source data management system which has a lot of the features of R and MATLAB in that we implement many of these off-the-shelf algorithms that people use, the building blocks such as linear algebra and statistics. But we do so with the mind that we are executing it at scale. And I'll get into more about what that means in a moment. So presently, the majority of the scientists we interviewed worked with hand-rolled solutions. This is to say that if we're lucky, they might start with R or MATLAB and then build their algorithms on top of it. But frequently, they even just roll C code from scratch. So this is challenging because it means that they're not necessarily optimizing for parallelism. They may not be trying to make it such that they make the best use of their I/O bandwidth or network bandwidth. They're also, frequently you just have one grad student, he writes his code, he does it to prove a very specific set of circumstances, and then he's done. This isn't extensible. It's not easy to build upon. And it's not very, and it can be quite ad hoc. So this reinventing of the wheel is quite troubling because it makes it hard to reproduce experiments and pass around data and, again, prove or disprove other hypotheses that might be related to the one that was initially studied. So enter SciDB. Here we built from a shared nothing architecture that, as I mentioned, has a large set of off-the-shelf operators for the common building blocks for science applications, which we learned from going out and actually interviewing scientists, building use cases, and abstracting away the most common themes. So SciDB works on a series of loosely coupled nodes over a shared nothing architecture. So this means that you take computers like the ones you would buy at Dell, you connect them via TCP/IP, and install Linux or a variant thereof. Now, this loosely coupled architecture is appealing for a variety of reasons. First off, it means that we can more easily scale out. We can simply work with many nodes at once, and there aren't strong dependencies as if you are sharing a disk. Or it also is good because it means that we can incrementally add or remove nodes, which will make for easier management of changing workload needs. And we'll talk more about this elasticity challenge in a minute. And the way it works also is it makes it seamless. It makes it so that scientists can focus on their work as opposed to software engineering. So if someone wants to submit a query, she will send it to a SciDB client, which has several array languages, array functional language, and array query language, which is very SQL-like. In addition, we support interfaces to R and C and C++ and Python. So they send their query to this coordinator node. And the coordinator manages the query, sending it to all of the hosts, each of which have different fragments of the data. So it assigns these query fragments to nodes, each of which contain different parts of the database. And subdividing these queries is another interesting challenge that we will touch upon shortly. So the other feature that makes SciDB very appealing for scientists is that it has robust support for user-defined functions. So that means that if you want to prove a new hypothesis, you make it very easy to plug it right into the engine and execute it over your data in the native database format. This makes it easier to share your results and build upon prior work. So from the perspective of a researcher, everything in SciDB is an array. And working within this multi-dimensional data structure makes it so that we can more easily optimize their queries as well as how they use hardware resources. Now, these examples are simple that I'm going to show you now, these two-dimensional arrays. But realize that in the majority of our applications, we're dealing with much higher dimensional space, and each of these arrays contain billions of data points. So it's much more challenging, but bear with me. So if we want to get started, we might create an array named image. And it has a single attribute, which is an integer. And here we say that it has two dimensions, I and j, each of which have values of 1 to 4. Now, once we've declared this array space, it can give us hints about how to both optimize the data layout and its distribution, as well as how to manage the queries. So say that the scientist now wants to select the upper left-hand corner, then he'll issue a between query, which will select this subarray from the image. After that, it produces a new image, which conforms to the same schema as was defined before. This makes the results comparable, easy to pass around, and the process of managing it more seamless for the user. Now, underneath the surface, the array data model is more complicated, of course. we start out by saying that we do have this dimension space. It is defined. But under the surface, many of our arrays are not actually densely packed. So in this example, you can see that we have a combination of both occupied cells as well as empty ones. And the occupied ones are where we have measurements. For example, if we're tracking whales, we want to look at where the whale was, and obviously the empty cells might be on land. So but we're still dealing in an n-dimensional space, and it's not like space just stops because we don't have a measurement there. So this means that we only store data where we have points so that we can better make use of the space. But also it means that the array may be of different physical size than we would expect if all of the cells were occupied. So this is another optimization challenge of organizing the data when it is not evenly distributed in logical space. So we ask the user for a third specification when he puts forth the schema for his array, which is a chunk interval. This third digit tells us the granularity at which we break up the data. So if the chunks are very large, that means that we might be able to bring in lots of data at once and save on disk seeks and I/O time. However, if they're too large, then it can be wasteful because we might overreach. Too small, and we might be able to manage memory at a finer granularity, but there's always trade-offs in this. In general, chunks are on the orders of tens of megabytes. So once he has these chunk strides, then...
So the chunk is something that I, as a researcher in physics, will tell you how?
Yeah, you tell me, like, do you think that you're accessing your data at a fine granularity or at a coarse granularity, roughly speaking? You tell me, like, that gives me a hint about how densely the data is packed. And it doesn't have to be perfect, and you can certainly change it later. But to the database, this array actually looks like this, because we break it down into strides in steps of 2. And by reasoning in these small n-dimensional subarrays, it makes it so that we can optimize our queries and still organize the data while preserving neighborhoods of points. So this is very important to actually make optimizations about the database that exploit properties of the operators, such as the matrix multiplication. Now, one thing you might notice is that this chunk has more data than all of the other ones combined. So this is an example of skew, and this is something that we very aggressively have to manage, that we want to bring in data. We want to organize our chunks such that we can more evenly access the data. Again, make better use of our I/O bandwidth. So another feature that we work with is that we use vertical partitioning. So that's to say that instead of our image having being a single array of integers, we have 3. We have red, green, and blue. So each of these is stored separately. Hence, when we execute a query, we only bring in the data that's actually going to be germane to the query. Because frequently, for example, with one data set I work with, which is a MODIS satellite imagery, they have 32 spectral bands that they take in. But most queries only access 1 or 2 of those bands. So this makes it so that we can further economize our use of the disk. Now, this also opens up opportunities for compression. For example, yes?
So I was wondering, could you compare and contrast this array model with something like classic high-performance Fortran, both in terms of like how the distributed arrays work, and because I mean, what you're showing in the previous slide is basically classic block distributed arrays, right? So
that's true, but
so and is the syntax basically an array syntax as well? So you're basically doing array operators?
Yes.
Okay.
So all of our syntax revolves around the array.
Right.
But with most of the Fortran style optimizations, I believe that they do like block cycles. You have fixed size blocks like this, but they're much smaller, whereas our blocks are a granularity of...
You choose it. You basically say,
yeah.
Here's my distribution, any variant of block cyclic,
Yeah, they do block cyclic, that's right. And we've evaluated block cyclic as well.
Okay.
But we'll get into more about how we often decompose into more complicated indexing schemes in order to optimize for a broader set of queries. So I've also done some work, which I won't talk about today, about optimizing the disk bottleneck for compression. And with this, we basically, by doing this vertical partitioning, we tend to co-locate arrays co-locate cells which share a value. And each of these coordinates, so if we have values that are stored together that are are similar to one another, this opens up a lot of opportunities to further encode and reduce our use of the hardware resources. So why bother with this complex model? Why don't we just build upon the commercial databases and extend relational technology? So just to work through an example of why this isn't the right thing to do, let's look at matrix multiplication using a relational database. And by the way, this is a real query execution plan that I evaluated. So you can see that we start out with matrix A. And to the relational database, it looks like this. We have a set of rows, each of which has an XY value and the contents of the cell at that coordinate. So if we want to multiply A and B, we first start out by sorting the data. We need to sort it in an order such that we can execute the individual multiplications of the rows transposed with the columns. So this is, if you're dealing with billions of cells, it's an n log n operation, but it's distributed and it's blocking. You have to do all of this before you can even start to issue any multiplications. So this just does not scale for large infrastructures. It results in serious performance penalties. So then after we've finally sorted it, we've gotten to an order where we can start actually multiplying the cells. Then we have to do all these comparisons. And this involves redistributing it over the network and emitting cells for addition. Then we have to do an additional sort, bringing together the cells that will be added here before we can finally start emitting tuples from the matrix. So this is very complicated. If you don't know anything about the order of the data, it can be quite costly. So to give you a taste for what the performance penalty is for this, some colleagues of mine have created a benchmark called GenBase, which does genetic expression data. And this GenBase, they went out and interviewed a group of cancer researchers and asked them, what are the most common queries that you execute? And then they baked off these queries with a variety of solutions. So in here, we're looking at linear regression over a very large data set. And you can see that we bake off distributed R against a column store and hand-rolled solution in which we plug in our relational database, and then we put in a hand-coded C++ operator on top of that. We then tried using distributed R with the column store so that we try to get the best of both worlds between the data management, managing the I/O and memory that we would for the database case, but optimizing the spatial operations using distributed R, and lastly, SciDB. So you can see that distributed R initially hits a wall when we first have only one or two nodes. This is because its in-memory representation is very inefficient. It's swapping, it's not seeing any performance gains, even though we add a second node. Once we get to a third node, it starts to realize the benefits of parallelism, but it still doesn't catch up with SciDB. Now, the column store plus hand-rolled really doesn't do very well with parallelism at all. It has a lot of overhead. It doesn't really actively manage the communication and the spatial aspects of the data. When we pair the column store with distributed R, we see that there's a near linear improvement in the rate at which we complete our query, but it still is limited because they have this massive in-memory representation of the data, whereas SciDB already performs fast. It has compressed the data extensively, so it fits into memory and only sees limited gains from the parallelism because we've already got it so fast. Basically, we are just bringing it in from I/O and then executing the query. So you can see that it scales more easily, whereas these other ones have significant overhead because they aren't using the array data model. So my first work revolves around optimizing queries. So here we ask the question of when a user submits a query, how do we fragment it, send it to the nodes so we minimize the end-to-end duration of the query? And this is ongoing work. We've published a very early version of it, but we are focusing on joining arrays for now. So when bringing arrays together, we have to think about both network as well as I/O and CPU time. So let's briefly work through an example. And this is actually a real query that we use, and that is for climate change. So one of the ways the earth scientists model the environment is by studying vegetation. They want to see where are there places where there's deforestation, and can we predict where it will happen further? So one of the things that they use for this is the normalized difference vegetation index. And in this query, we take two arrays, the first one being the visible red, and the second one being infrared, which is harder to see here. And we, but Okay, there we go.
Oh, we can't see infrared, so it should be.
Yeah, there you go. Yeah. So you can see that we take these two images, we superimpose them one on the other, and we calculate this difference divided by the sum. And by doing so, we get an estimate of the vegetation levels for a given location. So you can see that greater green shows that we have more vegetation, we have more trees here, and less greenery towards the middle where there are more people. So this is just a one-way join trying to bring together these two arrays, which may not be co-located. We need to compare individual cells. But we also want to learn about, over time, how the environment is changing. So then we have to think about how to coordinate this exchange amongst many, many arrays, all of which have different densities, perhaps, and different locations. So let's look at how we do that in SideBeam. So if we have our two arrays, and this is just a single chunk within the array, we have our lat and long, and we issue a query that looks like this, where we project the NDVI by taking the difference and dividing by the sum. And we select it such that where long equals long and latitude equals latitude. So this means that we iterate over our cells, and if there's a match, we emit a tuple, continuing with each one applying the NDVI equation. And we continue to fill it in. If there's not a match, then we have an empty cell. So you can see that this will be more sparse than its inputs. And so this is a pretty simple operation, but it gets much more complicated when we're dealing with thousands or millions of chunks and billions of data points. So when we broke this problem into two pieces. The first one is data alignment. So here we simply ask the question, for a set of chunks that need to be joined, are they on the same host? And the first step is we have to identify non-aligned chunks, ones that will require network bandwidth in order to execute the join. And after that, so we assign each of these logical chunks to exactly one node in order to produce the output. So you can see that in this case, we're basically doing round robin. We simply circularly assign one to each node. After that, we identify the ones that are already co-located and leave them where they are because network bandwidth is very expensive. So next, we execute the join, iterating each host will iterate over one chunk at a time and complete the operation that we looked at in the previous slide. So comparing the cells, emitting matches, applying the equation. So the thing here is that there are very different costs for each of these steps. So for data alignment, the network cost can be challenging because, first off, network bandwidth has not grown at the same rate as CPUs. I know that CPUs are starting to top off in their speeds, but they're still orders of magnitude faster to do a comparison than to ship something over the network. Secondly, this network bandwidth is shared. So when the data is being transmitted, the sender and the receiver is consuming resources, whereas CPU is eminently parallelizable with multi-core architecture. So this is another way that we can see performance gains on this side, but be more limited on this one. So after identifying this network bottleneck, we then started to think about how can we optimize our use of arrays in this space. So when we think about joins, one of our issues is that of skew, of course. And so take, for example, if we have a marine biologist, and she wants to understand how whales are being affected by commercial shipping lines. So she might want to join her whale sightings database, where she has a single array in latitude and longitude space with one of commercial ship tracks. And you can see here that the whales tend to congregate around the middle of the Hawaiian Islands, whereas the ships are largely at the ends. For example, cruise ships are pulling into Honolulu on a regular basis. They also tend to stop at the main island. So when we're thinking about how to align the data, how to assign chunks to nodes for the join execution, then we want to, if arrays have different hotspots, the inputs have different hotspots, then we want to identify opportunities where we can minimize our network bandwidth by moving sparser data around to the denser counterparts. Now, at the other end of the spectrum is adversarial skew. Now, to return to our vegetation index, one of the challenges with this is that the MODIS satellite imagery has a large column of sensors, each of which takes in light at different wavelengths. So when dealing with this, that means that wherever we have a sample for the red, we will also have a sample for the infrared. So each of the chunks that are being joined are of approximately the same size. So we can't really save on network bandwidth if they're not co-located, because this will cost it, because it costs the same no matter which host is executing it. So at this point, we need to turn our attention to optimizing, to load balancing CPU, because we can't optimize the network bandwidth. So in optimizing, yes? In optimizing our joins, we have devised two techniques. The first one is a shuffle heuristic, and the second one is a greedy algorithm. Now, each of these optimize about how to optimize different parts of the two-phase join. Now, the n-way shuffle works as follows. This heuristic is bringing sparser data to its denser counterparts. So it minimizes the use of network bandwidth, primarily optimizing the first phase of the join. So the way that this works is that in the SciDB, it has a storage manager, and this maintains the location of every chunk and how many cells are within it. So we iterate over each chunk and identify the one which has the smaller number of cells. The one that has a larger footprint becomes the host for the join. So again, we identify the sparser chunk and ship it to the denser, to the node hosting the denser join input. And we continue iterating over the array, assigning chunks to nodes on the basis of simply minimizing the network bandwidth. Now, you'll notice that this doesn't do anything to control for execution skew, though. It makes it so that we have to control this separately if we want to minimize the end-to-end duration of the query. So to this end, we developed an analytical cost model to describe how we're going to send different chunks to nodes. So if we are assigning n chunks to k nodes, then we first have to think about how long the data alignment phase will take. So we know that this is parallelizable. So for each host, we simply look at how many cells it will send and how many it will receive. Take the maximum of that, and then take the maximum over all nodes in order to see which one will be using the most network bandwidth. So that summarizes the highest cost for this phase. After that, then we look at join execution time. So here we look at how many cells are assigned to each host and take the maximum of that to see which one will have the highest CPU demands. We then estimate our join cost by putting these two together. We take the transmission number of cells and multiply it by the cost to send a single cell. And likewise, with the join, we say, okay, well, how much time does it take to compare and issue output for a given cell? And then we multiply that times the one that has the most cells. So by doing this, we can estimate the end-to-end duration for both phases, using both phases. So the greedy shuffler uses this algorithm as follows. We first use the n-way shuffle to minimize network bandwidth to give us a baseline to work from. But this, again, might have a longer total query duration, and we estimate the total query duration using the analytical cost model. So after we plan it, we identify the host that will take the longest, in this case, node 1, and identify the smallest chunk that resides on node 1. This will be the one that incurs the lowest penalty in terms of offloading it to a new host. We then ship it to the host that has the lowest demands on its time. And this will be, in this case, node 2. So node 2 takes on a greater CPU demand, and it does so while offloading things from the bottleneck. We repeat this process, reassigning the small chunks from the most burdened hosts until we achieve better load balancing overall. So you can see here now the network time is higher, but the total duration is less because we're more aggressively parallelizing the CPU time. So to evaluate this strategy, we experimented first with a set of arrays that were joining two arrays, each of which were 100 gigabytes in size, and assigning the chunks a Zipfian distribution. That's this power law distribution that we talked about earlier. So we started out with chunks that are of uniform size. That is to say that all of the chunks are of the same size. And here we see that our techniques perform quite comparably to the baseline, which in this case, the baseline is we reasoned about the arrays entirely at a time. We simply move the smaller array blindly to the denser array. Now, these are both of the same size for the uniform case, so it's a wash whether you move all of them at once, or whether you move A to B or B to A. Now, it also bears mentioning that this is how all commercial databases work these days, that they only move one relation to the other completely. They don't break it into pieces or do this fine-grained partitioning of the join like we are. So when we introduce slight skew, we see that our techniques start to produce gains. That first off, by bringing the sparse to dense, we see an improvement in our time, and we also, in our data alignment time, and we also see comparable performance in the join execution. As the skew starts to become more severe, we see even bigger gains. So we get to make more interesting decisions. So here we see that the n-way shuffle improves significantly by reducing network bandwidth. But then the greedy algorithm has further improvements by having a higher data alignment cost and a lower join execution. Now, once we get to severe skew, where the exponent on our Zipfian curve is 1.5, this is where things start to get less challenging, because here both of them arrive at the same solution. And we've tried several other techniques, all of which say converge that the network bottleneck becomes the primary cost as we get to severe skew. So that's interesting for just testing out the hypothesis, but let's look at this with real data, yeah?
Just wondering, so I'm assuming that when you did these tests, you knowingly selected a chunk size that would be good to show this, but the user might not have a really good idea of the chunk size that would be appropriate.
Uh-huh.
How much would this be affected by a user poorly
Choosing their chunk size? So we chose moderate-sized chunks. We subdivided the space into 256 equal pieces. It's 100 gigabytes of data. So, but if you had finer-grained chunks, we'd probably perform better because we could more evenly break up the skew. You know, we could optimize at a finer detail. But if you had coarser-grained chunks, then life would get more challenging because we would see less gains because we have to operate at this higher level. So yes, it is somewhat dependent on chunk size, but as long as you have many chunks, then you should be able to make good decisions. Yep?
So this is a natural join.
Yes.
I'm curious what happens when it's like a theta join. My scientists might want to write a cross covariance between two arrays.
Yes.
And so now you don't always have the array
Why?
decisions line up.
Yes, so
Does it improve, or?
to be honest, we have not conducted those experiments yet, but I would imagine that we are actually in the middle of a project where we have these multi-phase joins. And so far, it depends on a few things. I mean, you have to adequately estimate the cardinality of the intermediate results, right? You have to know the size of what you're shipping around after you've done your first set of comparisons. But with good statistics, you can still exploit this trade-off and reduce your network bandwidth. So let's look at this with real data. So here I analyzed joining two science applications that I have been studying, one of which is the Coast Guard ship tracks. And here we are looking at ships that are around the continental US. Every ship that approaches our shores has to have a beacon on it, which pings the Coast Guard and says how it's moving. And this is 3 years worth of data. It's 400 gigabytes. It has been used primarily for modeling coastal erosion as well as interferences with whales. So this is very skewed data. As you can imagine, the ships congregate in ports. So 85% of the data resides in just 5% of the chunks. It's extremely skewed, very concentrated, and hence harder to manage. So at the other end, we have the NASA satellite imagery. So here, the satellites are circling the Earth. They get a complete picture of the globe's surface every 2 days. So we have 14 days worth of data at 600 gigabytes. And this is much more uniformly distributed because we are covering the Earth's surface. So we first looked at a case of beneficial skew. Here we're joining the ship tracker data with the MODIS data. And in this case, we see about a 3x speed up with our approaches. because we simply bring the sparser chunks from MODIS to their denser counterparts. So at the same time, we also evaluated this vegetation index for adversarial skew. Again, we have the column of sensors, and they are each taking measurements at the same time. So the chunks are of the same size, limited opportunities to improve our query duration. So here we see that we do not lose generality in our approach and that we can perform quite comparably to the move small technique. Now, so this concludes my work on optimizing queries. Any questions before we go on? So my second thing that I'd like to talk with you about today is that of managing elasticity within SciDB. So SciDB uses a no overwrite data model. This means that scientists never want to throw away their measurements until they absolutely have to. So their database is constantly expanding. Hence, they need to add new nodes periodically in order to keep up with their storage demand. So in this work, we wanted to do two things. We first want to find a way to minimize the cost of operating. So we want to make it so that we expand the number of nodes that we need every time we have too much data and still have low cost overall in terms of both resources used and reorganizing the data when we expand. Now, at the second time, we want to maximize our parallelism when we distribute the queries. So we started by looking at several science applications and abstracting a workload model, looking at how do scientists interact with their data. So here, we note that they start with data ingest. They record a series of measurements and insert them in the database. If the database has free space, then they're all set, and they execute queries where they apply transformations to the data, putting it into a useful format where they can visualize it, where they can incorporate it into their pre-existing experiments, compare it to old data, as well as organize it for future studies. So that's the best case scenario, but sometimes they run out of space. And at that point, you have to add nodes and rebalance the data. Now this prompts two questions. First, we ask, how many nodes to add? How many do we need? And also, how do we rebalance the data in order to serve these spatial query workloads well? So we first approach the question of how do we decide when to scale out? And here you can see the demand for storage increases with each workload cycle. With each of these iterations where we ingest new data and process it into results, we need more storage. So we approached we use a leading staircase approach for this problem. So as you can see, we have provisioned this amount of storage. When we run out, we add k nodes, and then this serves the next several workloads. So this is workload specific, the amount that we expand. Essentially, we want to optimize P, the number of workloads that will be served, the number of inserts that will be served by our latest expansion. Now, when we optimize this, if P is too large, that means that we might overshoot, we might over-provision. If it's too small, it means we might spend all of our time reorganizing it because we expand on a very frequent basis. Now, when estimating how much data we will need for P workload cycles, we take it into account how much the demand has grown over the last S workload cycles. Now again, this is a trade-off which is workload specific, and we created a cost model for this as well, which I won't go into right now. But here we have S, and if we want to look back far enough, if we look back too far, then we might be sluggish in response to sudden increases in demand. But if we only look at the last few measurements, then we might be too volatile. So this is another decision to make. Overall, we optimize these decisions, optimize this cost model such that we minimize the total cost of ownership, which is to say that the number of node hours used will be minimized overall, where we say that if we have k nodes and we have j hours of work, then k times j is the number that we want to minimize. So after we decide how many nodes to expand by, then we have to think about how do we place the data in order to optimize our use of, yes?
Got a question on the node, picking how many nodes.
Yep.
So you didn't use, like you do with dynamic arrays, where you increase by some percentage of the size of the array. Is there a reason? I mean, they do that to avoid lots of copies, right? So you can have an amortized constant time.
Yeah.
So Is it because this happens less frequently you don't do that, or that you don't say let's go up every time by 10% of the size of our database, our existing database?
Well, rather than making it a function of the size of the database, we rather make it a function of the number of hours we believe we will use. So what we do is we go through here and we say, well, how long do we think the reorganization will take when we expand? How long do we think we're going to be executing our query workload? And we want to say that, okay, well, if we expand more aggressively, then we will see increased parallelism, and the number of node hours might decrease because we have executed our workload, because we are executing our workload at a faster range. But we did so with a higher network bottlenecks cost. So we rather optimize the total cost of ownership for this workflow rather than simply the size of the database.
So the number of nodes is not a constant. It is calculated based on some statistics.
So yes, the number of nodes is calculated by taking the slope of this curve and then multiplying it by p, the number of workload cycles that we want to provision for. So when thinking about how to redistribute the data over the nodes, we have several competing goals. The first one is that we want our scale-outs to be incremental. We only want to move data to the new nodes, the ones that are, so rather than globally reshuffling everything, which would be much more time-intensive. Now, at the same time, we aim to be skew-aware. So this means that we want to take into account the size of our chunks, rather than simply assigning the same number of chunks to each node. Lastly, we use spatial clustering. So neighborhoods of points should be co-located whenever possible so that things like k-nearest neighbors can run more quickly. So the first partitioner that we extended to this space is a KD tree. And this approach recursively subdivides the array space, iteratively cycling through dimensions. So let's work through an example of how that is done. So we first say we have this array, and we have 3 cells here. And we want each node to support 3 cells. So as we accumulate more data, we need to split the array. So we first find a point where there will be an equal number of cells assigned to each node. So here we say that we cut along the I dimension, and we say that where it's less than 5, it goes to node 1. Greater than 5, we go to node 2. We continue to accumulate points. And at this point, node 1 has a bigger demand. So we insert a new node and then iterate over this j dimension, identifying a plane where we can subdivide the space, again, splitting the node and rebalancing the data. So here we say that if we cut at j equals 8, then we can put an equal amount of data on either side. And this conforms to all of our expectations. It's incremental. Because we're splitting, we only have one node sending to several. And at the same time, it's also skew-aware, because we take into account the placement of these cells in array space rather than simply parceling out chunks one at a time to each node. It is also preserves these spatial neighborhoods. So we do so because we are range partitioning rather than a hash-based approach where we might subdivide by one chunk at a time. So for comparison, we've also, yes?
How do you know you want to choose J instead of I again? You can choose I to be 3 and still like 3 or less number, right?
Well, so KD tree cycles through the dimensions. So it does ij, ij, ij. And we do this so that each one is split an approximately equal number of times. So this, it could be limiting under some circumstances, but overall, it creates a good average case.
What's the advantage of like iterating for I and J?
Yeah.
How do you normally do that?
What?
What's the advantage of iterating over I and J instead of choosing by dimension?
Well, because you'll get if we have these spatial clusters, for example, if you're dealing with a cluster that looks like a circle, then you'll cut along both dimensions to get a more even distribution overall. Because usually these spatial clusters aren't just one long line of points. They tend to be clustered in their multidimensional space. So for comparison, we also created a uniform range partitioner. And here the aim is to, again, recursively subdivide the space, but we do so such that each host has an equal number of chunks. Now, this is more appealing for cases where the data might be more uniformly distributed, such as for the satellite imagery. So here we iterate through the dimensions, saying, cutting on I and then j and then I and j, until we have each of our chunks has one leaf node on the tree. So then when we insert one node, it takes the first half of the leaf nodes, and then the second one takes the second half of the leaf nodes. Now this is appealing because it still preserves the spatial neighborhood, but it does so in a way that, again, serves the uniform data. Now, if we expand to another node, we give them each an equal slice of the leaf nodes. But this does not give us our incremental placement, because again, you can see that all of them are shifting around the data. It also is not skew aware because we're only assigning chunks to nodes, an equal number of chunks, rather than simply doing then taking into account the location of the cells. But it does, again, have this n-dimensional clustering problem. So we baked this off with our two workloads. We interviewed scientists and drew from their use cases in order to identify a set of representative queries for the ship tracks and the satellite imagery. And we iterate through this workload cycle, inserting the data 1 day at a time for MODIS and 1 month at a time for AAS, which is the rate at which the scientists report the data. Now, here we evaluate the time it takes to reorganize the data as the database expands. Now, we start out with 2 nodes and add 2 at a time until we reach 8. And we also look at our benchmark time, as well as the degree to which we have balanced the data over the nodes. So we do this using a relative standard deviation, where we say that for a given partitioner, we have a set of partitions of size S1, S2, up to Sk. And we take the standard deviation of this distribution, divide it by the mean. So lower numbers denote a very even load balancing. So even distribution of the data over nodes. So you can see that the KD tree performs quite well in terms of minimizing our reorganization time and the workload time for the benchmark. But it does pay a penalty in comparison to the uniform in terms of organizing the data. So in terms of load balancing. So you can see that for a couple of reasons, it does not efficiently load balance our skewed data set, mostly because we cut across entire ranges rather than dealing with the actual cells. And this is partially a limitation of doing range partitioning, but also partially goes back to your question about the granularity of which we chunk the data. So we can't subdivide chunks. Thus, we can only divide as evenly as the granularity at which we are storing the data. So I just want to talk briefly about a couple of pieces of additional research that I am doing. So the first thing that we are starting to address is that of flexible chunking. So some colleagues and I at MIT are investigating making our chunks of the same size and serializing them by Hilbert curves or by the KD tree or other techniques such that they occupy different percentages of the array's space. This introduces several novel challenges for optimizing the queries, for laying them out on disk, but it will make it so that our use of I/O resources is much more even. And the other thing that I'm doing is extending this incremental model of elasticity to online transactional in-memory workloads, the HStore project. So here we are dealing with skew in the form of CPU bottlenecks. People are accessing very small queries, but doing so repeatedly. And for example, in the New York Stock Exchange, about 90% of the transactions are done on just 10% of the stock symbols. So we have very popular ones, so we have to manage the skew. And this behooves a 2-tiered scheme, which I'd be happy to talk about, data partitioning scheme, which I'd be happy to talk about offline. So another project that I'm in the process of initiating is that of personal data-driven decision-making. And this is a paper that has been conditionally accepted to VLDV's visions track. So I'm looking forward to sharing this with you. So this, basically, we've all heard about how big data is changing the game in evidence-based medicine, education policy, even business management. But in my opinion, we've been very slow to get these gains to everyday life. That I want to get to a point where I can use data to inform my decisions, to be able to create personalized queries so that the data can help me. So you can imagine that if you want to ask questions like, I'm planning a vacation to Jamaica, will there likely to be more sunny days in July or August? The data is definitely out there, but easily accessing it, understanding the probability distributions, that's much more challenging, especially if you're not a programmer. So I want to make it so that non-programmers can access these massive data stores. So these are highly personalized queries. They have context. They rely on extrapolating from examples of similar experiences in the past. And they rely on integrated models in order to draw conclusions about probable outcomes. So take, for example, if I want to know what is the projected value of my car if I sell it in N years. I'll get much better estimates if I take into account my commute, the rate at which I maintain the car, my driving record. And people are actually maintaining a lot of this personal information, but we aren't really adequately leveraging it right now. So just to walk through an example of how this might work. So say that you're Sally, a student, and she's graduating from high school, and she wants to know that if she gets a degree from University X, how much is this likely to boost her lifetime earnings? So this is a very personal question, because it relies on both Sally, the student, as well as the university to which she is considering matriculating. So you can imagine that that's the context within which she's working. She wants to know about students who are like her, not just all students. And so she wants to find databases which might be on, for example, government websites, as well as private data stores which sell access to their data, such as InfoChimps or Data Market, to learn about the outcomes of students who are maybe close to her in her GPA or her class rank and SAT scores. And although she doesn't know much about modeling, the database might recommend that she uses a k-nearest neighbors approach, where she identifies students that share characteristics strongly with her and then extrapolates from their outcomes. So you can imagine generalizing this to financial decisions, to choices about where to live and how to spend your time, and so on. So with that, I thank you.
Turn on the lights up.
Thanks.
Sorry.
Any questions?
I'm not sure how, so the research you were doing up until this last bit
Yeah.
was all about how to handle huge chunks of data.
Yes.
For someone like me who might be writing a MATLAB script to do it. And this last one is very
It's a
big.
departure, I
Yeah,
understand.
it's a departure. So, moving forward, are you sort of envisioning yourself more in that second realm, or more in the first, or
Well,
equal
a
realm?
combination of the two, to be honest. So I am both considering, well, so one thing that I found from working with all of these scientist studies, that on the whole, the last mile is the hardest. Even they have a lot of usability challenges for skilled coders. So I think that both of these have a lot of appeal in terms of making it just easier to work with your data, easier to access, and that they're easier to write queries such that you can inform the goals that you are working on. So I certainly see myself in both domains, that of trying to make it so that scientists can more easily access and work with their data, and that we can take lessons learned from that and bring it into everyday life.
So the intersection would be in the language, the way in which you express the queries,
Yes.
either as a common user or as a scientist.
Yeah. Yes?
Well, that raised an issue, again, some of us here are from the AI side of things, and that's why we sort of triggered on the last bit, which was over to very classic, modern, classic and modern AI. What made me wonder, to what extent, and do you know, either from personal exploration here or elsewhere, about the data query optimization characteristics of these more machine learning oriented type of problems, which tend to mostly focus on how can we, how much data do we have, what confidence will we have,
Yeah.
algorithms for converging, things like that. But I usually don't see them paying too much attention to the low level where that data is, except that we got a lot of it.
Yeah.
And how can we hold terabytes in memory or not? But I don't see them talking about optimizing a database for machine learning and other similar types of algorithms. Is there stuff done on that? Is that stuff
Yes,
that's
so
been done?
actually one of my colleagues at Brown has a project called MLBase, which is exactly this, optimizing machine learning meets data management. And they're much closer to a Hadoop-style model where they optimize the execution of these math-intensive operators. So that work is certainly being done, but it's outside of my particular domain. Yes?
So in the first part of your talk, you were kind of assuming a model where you have this massive amount of data that's just kind of sitting there and you want to run some analytics on it, right?
Yeah.
So what I've seen is a lot of scientists who are interested in things like in situ visualization, where you want to see or run analytics on your simulation, for example, as it progresses. So is that something that you can maybe address with your system?
Well, with the incremental elasticity, we certainly make provisions for people inserting their data as they go along and then doing processes on it in order to visualize the results and execute queries to compare it to the prior, so they can have an ongoing experiment. However, it is designed for more of batch inserts because most of these queries optimize on the notion that we are dealing with read mostly. So that means that if the data is moving around, we have to lock it, and we can't necessarily reason about where it's going to be spatially. So there's certainly a trade-off, and that's a high-level one of trying to decide how much do you want to accommodate writes and things moving around versus how much do you want to optimize the movement of data from disk and in memory. Yes?
So in your last future work talk,
Yeah.
you talk about you had inquired what's your future earnings based on your personal data.
Yeah.
I'm curious how you need to provide your personal data to the database. Have you considered about privacy issues in this case?
Oh, yes. So privacy in this context is really a two-way street. And it's challenging because on one hand, the data providers are increasingly valuing this as one of their core assets. Like a lot of Facebook's valuation is simply on the data that they collect. So on one hand, if I want to ask about the outcomes from people in their database, they want to protect their clients' privacy because otherwise their business will dry up pretty fast, right? But at the same time, I don't want them to know that I'm asking about that, say I had a crummy grade or something. I don't want to advertise that to Facebook, right? Or whomever is serving the data. So in this regard, there are a couple of techniques that I've been investigating in terms of differential privacy, which has a privacy budget, so you can tell how much, you can statistically ascertain how much information is being revealed. So it's also a matter of perhaps anonymizing when you submit the queries, so they don't have to know it's me who has these statistics.
Thank you.
Yes?
Selling on statistical analysis, I was wondering, coming back to your hypothetical scientific user, why do they have to set the chunk size? I mean, shouldn't this be something you should be able to run statistics on and figure out a good chunk size without the user ever having to see that?
Yes, and actually one of my colleagues wrote a paper on that, about how to select chunk size. And right now we're really generalizing the array model, so the chunk size was something to get us off the ground. And now we're starting to generalize the array model so that we can have these ones that are of a fixed physical size but varying logical size. So, I mean, yes, you still have to reason about the granularity. You have to say that my fixed physical size will be 64 megabytes or something. But we can learn about that by looking at how the data is accessed. Like, that's on my future work agenda, which is to say that, okay, if you're only making small selections, then you would want this chunk size to be small. But if you're making larger ones, then we want to amortize the cost of seeks in terms of bringing in a bunch of contiguous data at once, right? So there's certainly a tension there, and it is very workload dependent, but we have started studying that issue. Anything else?
Thank you.